A question from differential equation. We are given a linear differential equation with fx is a continuous function such that the limit of fx as x tends to infinity is 1. We have to find the value of the limit of x tends to infinity yx. Had this function been given, we would have solved the linear differential equation and found out the function yx, and we would have taken the limit. But we are not given the function f. The only thing we are given is f is a continuous function with limit of x tends to infinity fx is equal to 1. Let us proceed. The differential equation is linear and the complementary function is yx is equal to a e power minus 10x, where a is a constant. We apply the method of variation of parameters. We will take the particular integral as yx equal to ax e power minus 10x, where small ax is a function of x. We differentiate both sides, and as per the method of variation of parameters, we will take a dash x e power minus 10x to be f of x, and we integrate from x naught to x to both sides of this equation after taking this term towards the right. Note that this x naught, which is a positive number, always exists, so that whenever x is greater than x naught, fx is greater than 0. This is possible because f is a continuous function and limit of fx as x tends to infinity is 1. So on integrating, we get this form, and hence the general solution to the differential equation can be written in this form. Now we take the limit as x tends to infinity. This term goes to 0 and this term goes to infinity. This is by the limit comparison test for improper integrals of first kind. We will take e power 10t for the comparison. Now we can apply the L'Hospital's rule and Leibniz rule of differentiation under the integral sign to get this expression, and finally we will end up with 0.1. There is an easy solution to this problem. What we can do is we will take an example for fx which satisfies this condition. Let us take the simpler function. We consider fx equal to 1. This is a continuous function and it satisfies all the conditions for fx. We plug it there in the differential equation dy dx plus 10y equal to 1 and solve this equation, and we will end up with the same answer, that is 0.1. Now this we can do because whatever function we take for f, the result should come out to be the same number, otherwise this question is not valid. Thus this is a kind of questions where instead of solving the problem conventionally, we can use an example and then find out the answer in a much convenient way.